Welcome to this coding problem walkthrough. In today's session, we'll tackle problem number 1242, web crawler multithreaded. This is an exciting and practical problem that combines the concepts of multithreading with web crawling. Let's dive in and explore how to solve this step by step. A web crawler is a program designed to systematically browse the web, downloading and indexing web pages. In this problem, we are asked to build a multithreaded web crawler. The task involves starting with a given URL, referred to as the start URL, and using an interface called HTML parser to fetch all other URLs linked on the same page. The challenge is to crawl only the URLs that belong to the same hostname as the start URL. By using multiple threads, we aim to improve the efficiency of the crawling process. To achieve this, you'll need to implement a function called crawl that takes two arguments, the start URL and the HTML parser instance. The output should be a list of all URLs that share the same hostname as the starting URL. URLs follow the standard format of http://hostname/path, and the function should ensure that the crawling is efficient and thread-safe. Now, let's break down some key details of the problem. The hostname of a URL is the portion that appears after http:// and before the first /. The path is everything that comes after the hostname, which may sometimes be empty. When implementing the web crawler, you'll need to ensure that only URLs with the same hostname as the start URL are included in the result. It's also important to avoid revisiting the same URL multiple times, as this could lead to infinite loops or redundant processing. The order of URLs in the output doesn't matter, which gives us some flexibility in how we handle the results. The expected function signature for this problem is crawl, start URL, str, HTML parser, -list, str. With these rules, we can now explore some examples to clarify how the solution should behave. In the first example, the start URL is http://example.com/start. When the HTML parser's getURLs method is called on this URL, it returns three URLs, http://example.com/a, http://example.com/b, and http://example2.com/c. The hostname of the start URL is example.com, so the crawler should only include URLs that share this hostname. As a result, http://example2.com/c is ignored because it has a different hostname. The output includes the start URL along with the two valid URLs, http://example.com/a and http://example.com/b. The order of these URLs in the output does not matter, as long as all valid URLs are included. Let's look at another example. Here, the start URL is http://LeetCode.com/problems. The crawler begins by fetching two URLs, http://LeetCode.com/contest and http://LeetCode.com/discuss. It then crawls http://LeetCode.com/contest and discovers another URL, http://LeetCode.com/ranking. When the crawler visits http://LeetCode.com/discuss and http://LeetCode.com/ranking, no additional URLs are found. All the URLs belong to the same hostname, LeetCode.com, so the output list includes all of them, http://LeetCode.com/problems, http://LeetCode.com/contest, http://LeetCode.com/discuss, and http://LeetCode.com/ranking. This demonstrates the breadth-first nature of the crawling process, where we explore all reachable URLs within the same hostname. Finally, consider the third example where the start URL is http://news.ecombinator.com. When we call HTML parser.getURLs on this URL, it returns an empty list, meaning there are no additional URLs to crawl. Since no other pages are linked, the output is simply the starting URL itself. This case highlights that the crawler should handle scenarios where no further exploration is possible. Additionally, there are several constraints to keep in mind while designing the solution. For instance, the total number of URLs will not exceed 10,000, and HTML parser.getURLs will only be called for URLs that match the hostname of the start URL. The solution must use multiple threads for parallelism, and the output list must include all unique URLs that belong to the same hostname. While the order of the URLs does not matter, ensuring thread safety and avoiding cycles are critical for correctness. To begin addressing the problem, we first consider a brute force approach using a single-threaded breadth-first search, or BFS, and depth-first search, or DFS. The basic intuition here is to start crawling from the given URL and explore every page reachable from the starting point. To ensure we don't revisit the same page, we use a set to track visited URLs. BFS would allow us to crawl level by level, visiting pages closer to the starting point before moving deeper, while DFS would dive into links further down the chain before backtracking. While this approach is straightforward and works well for smaller tasks, it has several limitations. Single-threaded execution leads to inefficient use of time since network latency dominates, and there's no concurrency to parallelize the workload. As a result, this approach struggles with large-scale crawling tasks, where the number of URLs can be significant. The time complexity is linear, O(n), as each URL is visited once, but the lack of parallelism makes it slow in practice. Similarly, space complexity is also O(n), due to the storage of visited URLs, but the sequential nature of this approach limits its performance scalability. To overcome the limitations of the brute force method, we turn to a more optimized solution, multi-threaded crawling using a thread pool. By leveraging multi-threading, we can crawl pages in parallel, significantly reducing execution time. A thread pool allows us to manage a fixed number of threads, ensuring efficient use of resources while avoiding the overhead of repeatedly creating or destroying threads. To prevent issues in a concurrent environment, we use thread-safe data structures like a concurrent set to track visited URLs and a blocking queue to manage the URLs to be crawled. The process starts by parsing the hostname of the initial URL, which ensures that the crawler stays within the same domain. A fixed number of threads are then launched, and each thread fetches URLs from the queue, retrieves their content using the HTML parser, and identifies new URLs to add back to the queue, provided they're from the same domain and haven't been visited. This cycle continues until every thread finishes processing and the queue is empty. By parallelizing the network requests, we reduce the impact of latency, and thread-safe operations ensure correctness. Overall, this approach achieves a balance of performance and resource management, making it highly effective for moderately large datasets. This approach is particularly compelling because of its balance between simplicity and efficiency. It scales effectively to handle a moderately large number of URLs while ensuring correctness through the use of thread-safe operations. The time complexity remains O(n), as each URL is processed exactly once, and the space complexity is also O(n), accounting for the visited URLs in the queue. However, the real advantage lies in its ability to leverage concurrency, which drastically reduces the execution time compared to a single-threaded approach. By maintaining this balance, the multi-threaded crawling strategy provides a practical solution for real-world crawling tasks where scalability and performance are key. The multi-threaded crawling approach using a thread pool was chosen because it effectively leverages concurrency to address the inefficiencies of the single-threaded method. While the sequential approach is simpler, its poor performance due to network latency makes it unsuitable for large-scale tasks. The multi-threaded approach, on the other hand, achieves significant performance gains by parallelizing URL fetches, making it scalable for larger datasets. There are trade-offs to consider, such as the overhead of managing threads and the higher memory usage associated with concurrent data structures. However, these are outweighed by the benefits of reduced crawling time and resource efficiency. Fully asynchronous implementations, like those using non-blocking I/O, could further optimize performance but come with added complexity in debugging and implementation. By comparison, this multi-threaded strategy strikes a balance between performance and simplicity. The key insight here is that the time spent on network requests can be drastically reduced by parallelization, and by constraining the crawler to a single domain, we maintain focus and ensure compliance with the problem constraints. This approach is robust, scalable, and efficient, making it the ideal choice for solving this problem effectively. To solve the web crawler multi-threaded problem, we need an algorithm that systematically traverses web pages starting from a given URL. The goal is to fetch all reachable pages while avoiding infinite loops caused by revisiting the same pages repeatedly. For this, we can use either breadth-first search, BFS, or depth-first search, DFS. but here we focus on BFS for structured traversal. The first step is initialization. We'll create a visited set, which keeps track of URLs we've already processed, ensuring we don't revisit them. Next, we initialize a queue, which is essential for BFS traversal as it allows us to process URLs in the correct order. The starting URL is then added to both the visited set and the queue to kick off the crawling process. Once initialization is complete, the BFS traversal begins. As long as the queue is not empty, we repeatedly dequeue URLs, starting with the front of the queue. For each URL, we fetch its HTML content using a web scraper like requests.get in Python. The next step is to parse the HTML to extract all hyperlinks from the page, which can be done using tools like Beautiful Soup. These links are then filtered to ensure they meet specific conditions, such as belonging to the same domain, and duplicates or links already in the visited set are removed. Valid links that pass these checks are enqueued into the queue and simultaneously added to the visited set to mark them as processed. This process of dequeuing, fetching, parsing, filtering, and enqueuing continues until the queue is empty, which signifies that all reachable pages have been visited. BFS is particularly suited for this problem because it processes links level by level, visiting the nearest neighbors first. This behavior is useful when analyzing the depth of the web graph or ensuring a structured traversal. A key feature of the algorithm is the use of the visited set, which prevents revisiting the same URLs, effectively avoiding infinite loops that could arise from circular links. The algorithm also scales well, as BFS can be parallelized across threads or processes. For example, different threads can handle separate segments of the queue, allowing multiple pages to be crawled simultaneously. Handling edge cases is equally important. Dead links, such as those resulting in HTTP 404 errors, should be skipped to prevent interruptions. Redirects need to be followed correctly to avoid missing valid pages, and duplicate links must be normalized, such as by stripping unnecessary query parameters, to ensure each page is processed only once. The choice of data structures is critical to the efficiency of this algorithm. The visited set is used to track URLs that have already been processed, and because it offers constant time lookup, it ensures we avoid revisiting pages, even when there are millions of links to process. The queue is the backbone of the BFS approach, maintaining URLs to be processed in level order. This ensures a structured, breadth-first traversal of the web graph. Finally, an HTML parser like Beautiful Soup is used to extract links from the HTML content of each page. This parser provides a reliable and structured way to identify and filter hyperlinks, ensuring that only relevant links are passed to the next stage of the algorithm. Analyzing the complexity of this algorithm helps clarify its efficiency. The time complexity depends on the number of pages to visit, n, and the average time to fetch and parse each page, p. Since we process each page exactly once, the total time complexity is O, n*p. Space complexity is determined by the storage requirements of the visited set and the queue. In the worst case, both the visited set and the queue can grow to store all n URLs, resulting in a total space complexity of O, n. By understanding these complexities, we can better evaluate the algorithm's scalability for large-scale web crawling tasks. Here, we begin by importing the necessary modules, threading for managing multiple threads and queue to handle the URL queue. Inside the solution class, the crawl method is defined to perform the web crawling. First, we have a helper function get_hostname that extracts the hostname from a given URL. This is essential for ensuring that we only crawl URLs within the same domain as the starting URL. Next, we define the worker function, which represents the task each thread will execute. This function continuously processes URLs from the queue until it encounters a none signal, which marks the end of processing. For each URL, it checks whether it has already been visited. If not, it adds the URL to the visited set while using a thread lock to ensure thread-safe access. Then, it fetches all new URLs linked from the current page using the HTML parser.getURLs method and adds them to the queue if they belong to the same hostname. Finally, we initialize some critical variables: hostname to store the domain of the starting URL, visited to track the URLs we've already crawled, and locked to manage thread-safe operations. Now, we initialize the queue to manage the URLs to be processed, starting with the initial URL, start URL. To enable multi-threaded crawling, we create a list to hold threads and start 8 worker threads, each running the worker function. These threads work in parallel, processing URLs from the queue. Once all URLs have been processed, signaled by the queue being empty, we send a none signal to each thread to indicate that they should stop. Afterward, we join all threads to ensure they have finished executing completely. Finally, the method returns a list of all the visited URLs, which represents the result of the crawl. This implementation efficiently leverages multi-threading to perform web crawling while ensuring thread safety and restricting the crawl to a single domain. Here, we begin by defining our Java implementation for the web crawler. First, we import the necessary packages, including java.util** and java.util.concurrent**, which will enable us to use collections and multi-threading. The main method, crawl, takes in a starting URL and an HTML parser object. Within this method, a helper function called getHostName is defined to extract the hostname from a given URL. This allows us to identify whether a URL belongs to the same domain as the starting URL. We then initialize a thread-safe concurrent hashmap set called visited to track URLs that have already been processed. The start URL is immediately added to this set to avoid revisiting it. Next, a blocking queue is created to store URLs that need to be crawled. The start URL is also added to this queue. To enable multi-threading, an executor service with a fixed thread pool of 8 threads is initialized, which will allow us to process multiple URLs concurrently. A list is also created to store the futures associated with each thread. Finally, a runnable worker task is defined. In this worker, we repeatedly poll the queue for URLs to process. If a URL is retrieved, we ensure it's not null before proceeding to process it further. Now, within the worker task, we use the HTML parser object to fetch the list of URLs linked to the current URL. For each new URL, we check if its hostname matches the original starting URL's hostname, ensuring we stay within the same domain. If the hostname matches and the URL hasn't been visited yet, we add it to the visited set and enqueue it for further crawling. After defining the worker task, we submit 8 instances of this task to the executor service, creating multi-threaded execution. The futures list stores references to these submitted tasks, allowing us to monitor their progress. Once all tasks are submitted, we use a loop to wait for each task to complete. If any exceptions occur during task execution, they are caught and printed. This ensures that all threads finish processing before we proceed further. Once the tasks are completed, we shut down the executor service to release resources and signal the end of the thread pool. Finally, the method returns a list of all visited URLs by converting the visited set to an array list. This ensures that the output matches the problem's requirements and represents all unique URLs crawled within the same domain. Finally, the problem specifies a mock interface called HTML parser, which we include here to ensure the code compiles correctly. The HTML parser interface defines a single method, getURLs, which takes a URL as input and returns a list of strings representing all the URLs found on that page. This interface is assumed to be implemented externally, as it's provided in the problem description. The crawl method relies on this interface to fetch the URLs from a given page, making it a critical part of the web crawler's functionality. By adhering to this interface, the solution remains modular and compatible with the problem's constraints. This concludes the implementation, showcasing how multi-threading and thread-safe collections work together to efficiently crawl web pages within the same domain. In this example, we are given a starting URL, http://example.com/start. The goal is to crawl all pages within the same domain using multiple threads. First, we extract the hostname from the starting URL, which is example.com. Then, we set up our data structures, a set called visited to track URLs we've already processed, and a queue to manage the URLs waiting to be processed. Initially, we add the starting URL to the queue. Finally, we create 8 threads that will work concurrently to process the URLs in the queue and explore the web pages. The first thread begins by taking http://example.com/start from the queue. It adds this URL to the visited set and uses the HTML parser to fetch its outgoing links, which are http://example.com/page1 and http://example.com/page2. Since both URLs belong to the same domain, they are added to the queue for further processing. Meanwhile, the second thread picks up http://example.com/page1 from the queue, marks it as visited, and fetches its links. This URL points back to the starting page, but since http://example.com/start is already in the visited set, no further action is taken. Similarly, a third thread processes http://example.com/page2 adds it to visited, and retrieves its outgoing link, http://example.com/page3 which is added to the queue for future processing. As the fourth thread processes http://example.com/page3 it adds this page to the visited set and checks for any outgoing links. Since there are no further links returned by the HTML parser, this thread completes its work here. At this stage, all threads continue working until the queue becomes empty. Once all URLs have been processed, the program terminates. The final result is a list of all unique URLs within the same domain, which in this case are http://example.com/start http://example.com/page1 http://example.com/page2 and http://example.com/page3 Now, let's consider a scenario where the starting URL belongs to one domain, but some of the links lead to different domains. Here, the starting URL is http://site.com/home and the hostname extracted is site.com. We initialize the visited set and the queue as before, adding the starting URL to the queue. When the first thread processes http://site.com/home it adds the URL to the visited set and retrieves its outgoing links, http://site.com/about and http://othersite.com/contact. The link http://site.com/about shares the same domain as the starting URL and is added to the queue, but http://othersite.com/contact is ignored because it belongs to a different domain. In the next step, another thread picks up http://site.com/about from the queue, marks it as visited, and fetches its outgoing links. The only link it returns is http://site.com/home, but since this URL is already in the visited set, no further action is needed. At this point, the queue becomes empty, and all threads finish processing. The final result includes only the URLs that belong to the same domain as the starting URL, http://site.com/home and http://site.com/about. Finally, let's look at an example with circular links. Here, the starting URL is http://circle.com/start, and the hostname extracted is circle.com. After initializing the visited set and the queue, we add the starting URL to the queue. The first thread processes http://circle.com/start, marks it as visited, and retrieves its outgoing link, which is http://circle.com/page1. This link is added to the queue. Next, another thread processes http://circle.com/page1, adds it to visited, and fetches its outgoing link, which points back to http://circle.com/start. Since http://circle.com/start is already in the visited set, no further action is taken. Once the queue is empty, the program terminates, and the result is a list of URLs within the same domain, http://circle.com/start and http://circle.com/page1. To analyze the time complexity of the multi-threaded web crawler, we start by breaking down its core operations. First, fetching URLs is a key step. The HTML parser.getURLs URL method is called for every URL within the domain, and since each web page contains an average of k links, the time spent fetching URLs across n unique pages is proportional to O(k*n). Next, checking if a URL has already been visited is handled via a hash set lookup. This operation is O(1) on average, and over the n unique URLs, the total time spent is O(n). Finally, inserting URLs into the queue involves enqueuing links from each page. While all k links per page may initially be added, each URL is processed only once, meaning the number of enqueue and dequeue operations is proportional to O(n). These components give us a framework for understanding the time complexity of the crawling process. Thread management is another factor to consider. Operations like starting, stopping, and synchronizing threads introduce constant overhead, which does not scale with the input size and is therefore O1. When combining all operations, the dominant factor is URL fetching, which requires O(k*n) in the worst case. This makes the overall time complexity O(k*n), where n is the number of unique pages and k is the average number of links per page. Shifting to space complexity, the first major contributor is the visited set. This hash set stores the n unique URLs, with each URL requiring O1 space. As a result, the total space usage for the visited set is O(n). Similarly, the queue, which manages URLs to be processed, may also hold up to n unique URLs in the worst case, contributing O(n) to the space complexity. Threads are another consideration for space complexity, but the number of threads is fixed 8 in this implementation, which means the memory overhead for managing threads is constant, or O1. Additionally, each URL string occupies memory proportional to its length. If the average length of a URL is L, the total memory required to store all n URLs would be L*n. Combining all these, the primary contributors to space complexity are the visited set and the queue, both of which scale linearly with the number of unique URLs, resulting in an overall space complexity of O(n). Now let's consider the best, average, and worst case scenarios. In the best case, every page in the domain has no outgoing links, meaning k equals 0. Here, the crawler processes only the starting URL, leading to a time complexity of O1 and a space complexity of O1. In the average case, each page contains k links, and there are n unique pages to crawl. The crawler processes all n pages and their links, resulting in a time complexity of O(k*n) and a space complexity of O(n). Finally, in the worst case, all n pages have the maximum number of links, and every link remains within the same domain. This results in the same asymptotic time complexity of O(k*n) and space complexity of O(n), as the crawler must process all links while managing the same number of unique URLs. To put this into perspective, a naive approach using a single-threaded BFS or DFS would have the same time complexity of O(k*n), but without multi-threading, it would be much slower in practice. The multi-threaded approach improves performance by dividing the workload across multiple threads, in this case, 8 threads, allowing for concurrent URL fetching. While this approach does not change the overall asymptotic complexity, it significantly reduces runtime. The synchronization mechanisms used to ensure thread safety introduce negligible constant overhead. To summarize, each URL is processed exactly once, resulting in O(n) operations for visiting unique URLs. Fetching links from n pages takes O(k*n), with enqueue and dequeue operations bounded by O(n). The dominant factor remains O(k*n) for time complexity, while space complexity is O(n), driven by the visited set and the queue. When working with web crawlers, there are several common mistakes that can occur, and it's important to understand both why they happen and how to fix them. For example, cycles in the web graph can lead to infinite loops during traversal. This happens when pages link back to each other, such as page A linking to page B and vice versa. The solution is to use a visited set to track URLs that have already been crawled, ensuring you don't process the same page multiple times. Another frequent issue is ignoring domain restrictions. When the problem specifies that only pages within the same domain as the starting URL should be crawled, failing to enforce this can result in unnecessary or incorrect exploration. The fix here is to verify the domain of each URL before adding it to the queue. Inefficient parsing of HTML for links is another pitfall. Using unreliable methods like regular expressions for link extraction can lead to bugs and poor performance. Instead, use robust libraries like Beautiful Soup in Python or JSoup in Java for accurate and efficient parsing. Lastly, not handling edge cases like empty or invalid URLs can cause crashes. Adding proper error handling ensures that the crawler skips malformed URLs gracefully, avoiding undefined behavior. Additionally, overloading the server with too many requests in a short time is a significant mistake. Servers may block your IP if they are overwhelmed, so introducing a delay between requests, for example using time.sleep in Python, can help mitigate this risk. Now, when preparing for interviews, it's crucial to understand the trade-offs between BFS and DFS. BFS is generally preferred for web crawling because it processes pages level by level, which aligns well with breadth-limited exploration. On the other hand, DFS can lead to deep and unbalanced exploration, which is less practical in this context. Scalability is another key topic. Be ready to discuss how your solution can handle millions of pages, potentially involving multi-threaded or distributed approaches. Robustness is also vital. Ensure you emphasize how your solution handles broken links, cyclic references, and network timeouts. Finally, optimizing for real-world constraints is critical. Strategies like limiting the depth of the crawl, implementing rate limiting, and respecting robots.txt files demonstrate an understanding of practical limitations and best practices. To deepen your understanding, consider related problems that share similar concepts. For example, LeetCode 269, Alien Dictionary, involves graph traversal to determine the order of characters in a custom alphabet. This problem emphasizes dependency resolution, which is similar to managing traversal order in web crawling. LeetCode 133, Clone Graph, also explores BFS and DFS while requiring cycle detection, a key concept in avoiding redundant processing in web crawling. Another relevant problem is LeetCode 417, Pacific Atlantic Water Flow, which involves multi-source BFS or DFS to determine which nodes, or regions, are reachable from both the Pacific and Atlantic Oceans. This highlights the importance of identifying reachable states efficiently. Finally, LeetCode 841, Keys and Rooms, is a graph traversal problem that requires visiting all reachable nodes, akin to ensuring you explore all accessible pages in a web graph. These problems reinforce the skills needed for web crawling while broadening your perspective on graph algorithms. There are also alternative approaches to web crawling, each with its own advantages and trade-offs. Multi-threaded crawling, for example, can significantly speed up the process by allowing multiple threads to process URLs in parallel. However, this introduces the need for careful synchronization to avoid issues like race conditions or redundant processing. If you're dealing with large-scale crawling tasks, distributed crawling may be a better option. By spreading the workload across multiple machines, you can scale your solution to handle millions of pages. The trade-off here is the added complexity of coordinating tasks and merging results from multiple sources. Heuristic-based crawling is another option, where URLs are prioritized based on specific criteria, such as relevance or depth. While this approach can make the crawl more targeted and efficient, overly restrictive heuristics may cause some pages to be missed. Understanding these trade-offs is essential for tailoring your solution to different scenarios and constraints. Great job following along. In this problem, we explored how to use multi-threading to improve the efficiency of a web crawler. By leveraging BFS or DFS and ensuring thread safety, we were able to design an effective solution. Don't forget to practice similar problems to strengthen your understanding. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!